Hei! Velkommen til Universitetsbiblioteket og Geoonsdag i dag. Dette igjen vår siste Geoonsdag for i år. Og i dag har jeg den utsøkte gleden til å ønske velkommen Norbert Pirk. Og han vil holde sitt foredrag på engelsk, derfor gjør jeg også introduksjonen og videre på engelsk. So, Norbert has been born in Berlin, just behind the Iron Curtain, he told me. This means East Berlin. And studied physics there in Berlin, and then later on in Sweden, in Umeå and in Lund. And he has, after the physics study, worked a little bit in industry, with wind industry and particle physics. Very interesting topics you had. And then picked up the interest in land-atmosphere interaction in the Arctic and wrote a PhD there on Svalbard. And about this, it started the postdoc here at the Department of Geoscience, and where he is employed today as a researcher. And he was actually a vicar for John Burkhardt, professor in hydrology, sitting here for the period. And he is involved in our purchase of drones, and he is involved in designs. Very broad interest, and the most important thing that he succeeded to get a very high-ranked scholarship from the Norwegian Research Council, Young Talent Scholarship for his research, which I guess we will see some examples on today. And today's topic from Norbert is Tundra meets atmosphere, understanding the carbon and energy exchange. So, Norbert, the floor is yours.
Thank you. Can I take that? You? Right. Thanks, Bernd, for the nice introduction. Thank you all for coming. So today I wanted to talk about what happens exactly at the interface where the land meets the atmosphere, where the tundra meets the atmosphere, and why this is important for climate science and how we even got to know what we know today. So I thought I'd give you a small reminder, a recap of what this tundra is again. So tundra is a word from Russian Sami, which means the treeless uplands. So it's basically a word that we use to describe areas which are too cold for trees to grow. And the tundra is mostly found in Arctic areas, but also in the Antarctic, and in alpine high altitude areas. So it covers about 5 to 7% of the global land surface. And you also often hear words like permafrost or Arctic or wetlands in combination with the tundra. So I think it's important to notice that many times these words are almost used as synonyms. But oftentimes also there are quite important differences, that not everything that is permafrost is tundra, not everything that is tundra needs to have permafrost, not all permafrost is in the Arctic, and all of this. There is this intersection, which is a very interesting point to research, but not everything is exactly the same. So I said that these areas are treeless, and they are, but they are still vegetated. So there are still small shrubs and grasses growing there, and they die at some point. And this organic matter is oftentimes accumulating in these areas, or it has been accumulating over centuries or millennia in some areas, because it's not decomposed by microorganisms. It's either frozen in the permafrost or it's underneath the water table. So the microbiological activity is just not strong enough to decompose it like it would maybe outside here. So that is why this is a very interesting topic to research. And we also have to look a little bit into how much carbon there really is in these areas. So if you look at the figure from the previous assessment report of the IPCC, it says that 1,700 petagrams of carbon are now locked in the permafrost, which, if you compare it to the atmosphere, is about double as much as is in the atmosphere. It's about 3 times as much as is in all vegetation on the land surface. And it's a little bit more than what we have in all fossil fuel reserves at the moment. So it's a big carbon stock, of course. And it's not only big, but it's also only there because it's frozen. It is the reason for it being there is that it is locked up in the permafrost. And now that the permafrost is starting to thaw up, some of this permafrost carbon could be released as greenhouse gases to the atmosphere, where they would trap even more energy and heat from the sun. And then the atmosphere would warm up with that, which would lead to more thawing. So you get this kind of feedback loop that is really interesting and to some degree dangerous. And these feedbacks, I don't know if I can test this with this microphone. So basically what happens is that you have a small disturbance and you get an easy amplification, a self-amplification. The signal amplifies itself. And this is, in geosciences, these are the important processes that you have to check out. So it has obviously been recognized both by the scientists and by the media, and there's numerous articles every day coming out about this topic. Now we have acknowledged that we might even approaching some kind of tipping points, where at some point what happens is that exactly what I did with this feedback here with the microphone is that the system basically comes completely out of its stable state, or relatively stable climate state, and really turns into something else entirely. And this is what we are researching now. But between all of these sources of information, the news and our articles that we read every day, of course the IPCC Assessment Report 6, which was quite recently published, gives a very good overview of what's happening. And in there, this sentence here really caught my eye, where they argue that despite the accumulating evidence of increased carbon losses, it is still difficult to scale up site and ecosystem level measurements to assess the net carbon balance over the entire permafrost region. And this is due to the high spatial heterogeneity, strong seasonal cycles, and difficulty in monitoring these regions consistently across the year. And I'm going to go a little bit into detail of what I think they mean with this sentence and why I think it resonates very well with the research that we're doing at the Department of Geosciences. So what is it that makes this tundra so complex? What is it that causes these problems? One point to start to understand this is maybe if you ask the question of why there is even permafrost in the ground. Why do we find permafrost some areas and not other areas? And the answer to this is the surface energy balance. Because if you have a piece of surface, this surface partitions the available energy, the incoming energy from sunlight and the heat from the atmosphere, and it partitions it in some way, and some of it goes into the ground. So this surface energy balance is really determining, or it determines the soil temperature and thereby the presence or absence of permafrost. And this is obviously also connected to the water balance, because some of that energy loss that you get from the surface is actually evapotranspiration. It's a latent heat flux. It's water that carries or that removes energy from the surface. So together with a sensible heat flux, this evapotranspiration is actually the main or one of the most important boundary conditions for the atmosphere as well. So these surface processes not only determine what happens in the soil, but they also determine what happens in the atmosphere. And this in turn is also coupled to the carbon cycle, because depending on the water level, some areas in the soil might have access to oxygen and others don't have access to oxygen. And this really changes the entire microbiological cycling in the soil. So it determines whether the carbon that sits in the soil could be released as methane or as CO2. So all of this is really tightly coupled. So I hope you know why this is important to study now. And one question is, of course, how can we measure these gas and energy exchanges, and how can we then validate global data sets, such as satellite products or climate model output? So if you have a surface where you suspect that there's some gas exchange, maybe some CO2 coming out, what you can do is put a box on it. You trap some gas and see if the gas concentration of CO2 inside the box changes. If it, for example, increases, that means that there must be some CO2 coming out of the ground. And this can be done, and you can write a whole PhD about it if you want to. And you can see, for example, how we do this in an automatic setup in the polygonal tundra on Svalbard. Now, one problem with that approach is that we have this extreme spatial heterogeneity in this area. So on the scale of 1 meter, the fluxes can change by orders of magnitude. So for example, this chamber here was a strong methane hotspot, whilst this chamber here in the middle of the pond did not emit any methane in the 5 years I was there. It really changes from point to point, and that makes it quite hard to validate global products which see this entire landscape as 1 pixel. So depending on where you put your chambers, you really have to be careful not to pick up a bias. So that kind of got us to the insight that it would be nice if we could scale up this and kind of assess the overall carbon exchange and the overall fluxes in the entire area. And I mean, we are creative scientists, but we still like boxes very much. So what we do is we put a bigger box on it, but this time it's a virtual box. So this box is just in our heads, so that the wind can go through it and the sun can shine through it and heat the surface. And then we can simulate how the gas is transported and how energy is also transported away from the surface and into the atmosphere. So here you see the results of the temperature field from a large eddy simulation. So this is a cross-section of this box, and you can see how the turbulence really mixes up this energy and brings it into the atmosphere. So this turbulent mixing is the most effective transport process for both energy and gas exchange. Now, I know that this is a popular scientific talk, so I thought it was wise to explain even more about this, because what we normally do is that we don't have access to such nice cross-sections. We have maybe 1 sensor which we can put in the flow field. But this sensor can not only measure the temperature, but it could also measure the wind. So this 1 sensor we can put there and really record the time series of the turbulence transport. And you can already see here from these short time series that there's a correlation between the temperature and the wind field. I've plotted this here also for you. So you see how there's a tendency in our data set, for this case here, for air that moves upwards to be warmer than air that moves downwards. So these turbulent eddies, they constantly move up and down and in a seemingly chaotic way. But there's tendencies in these data sets. And if you have a heat flux on the surface, you would find such a correlation. You would see that air that comes from below is warmer than air that comes from above, at least in the tendency. So these correlations is really what we are hunting for. And we do this in real life. So here you see 150 meter eddy covariance tower in Sweden, which measures over a boreal forest here. That where you have basically where you put sensors into the flow field. You can do the same thing above the tundra. There you don't need a 150 meter tower. It's a few meters are enough because your canopy is a lot shorter. You don't have 10 meter high trees. You have only 10 centimeter high grasses. So here on top of this mast sits an anemometer, which does the exact same thing. And this hunt for correlations is a global business. So there's 200 to 300 stations that record these correlations as we speak. And these correlations are then used with this distribution to to validate satellite products, to tune parameters in our Earth systems, and to improve the climate projections. Now, this is a little bit of an outdated map of the FluxNet network, but you see that there's not terribly much going on in Norway. There is this one yellow dot, which is already in Sweden, and this one green dot, which is on Andøya, and so that site doesn't exist there anymore. So with that motivation that we should really represent Norway better, we, a few years ago, installed a flux tower in the Alpine Tundra at Finse. So we are on Hardangervidda, just 10 kilometers north of the Hardangerjökull glacier, where we put such an eddy covariance tower. We also got funding for a mobile flux tower, which is almost like a twin or a sister instrument that measures the same thing, but we can move it around in Norway. And these flux towers, they constantly year-round estimate or measure these correlations. They do that in all kinds of weather, in really harsh conditions, in really unpredictable conditions at Finse. We do that year-round, and we can see the data ticking into our servers every half hour. And then we can actually go in and see when does the tundra emit CO2 and when does the tundra take up CO2. So at what time of the year and at what time of the day do we get a release of CO2, which would be these blue areas. And maybe during the middle of the year and during the middle of the day, you see these red areas, these red fluxes, which are carbon assimilation. So carbon goes into the ground. And we can do that over years. And one question that we then always get is, oh, is this tundra, is this ecosystem now a source or a sink of carbon? Does it emit carbon or does it take up carbon? And at Finse, the story is quite interesting because you can then go in and basically sum up all these fluxes that you measure in 1 year, which you see here as a cumulative plot. And you can see how this varies between different years. And here, for example, at Finse, where 2019 was an ordinary year with a snow melt at some point in early June, we see that the ecosystem was a carbon sink. So it took up 20 grams of carbon per square meter in this year. Whilst the next year, which was an extremely rich, snow-rich year in the mountains here, it actually released CO2 because the growing season did not start as early as it did in a normal year. Now, we've done the same exercise at Palsameyers in Finnmark. So we moved our mobile flux tower to this area here, which is a typical area for discontinuous permafrost zone. So you would have these pulsar areas, these elevated mounts that have a frozen core, and you would have permafrost-free areas like this fan there, which does not contain any permafrost. And again, we did these measurements here for 3 years. You see for CO2 a very similar dynamics of carbon uptake and release. And for methane, you can, for example, see that there's more emissions during the summertime, but there's no diurnal cycle in it. And then we sometimes like to do what we call space for time substitutions. So we argue that as the permafrost at this site degrades, these pulsars would turn into open fan areas. So the carbon release from the pulsars you would accumulate more CO2 as these pulsars saw, but you would emit more methane. And these are, of course, very interesting questions to answer. And we can do this as researchers. We do this for a number of years. But if you want to do it, or some players in society, of course, they want to have this over long term. They want to have decades-long monitoring of this. They want to basically monitor such mires as they degrade. And this is something where we sometimes come to our limits because we cannot really, we have this grant cycles of 4 or 5 years, and then we can't really continue measuring over decades. This is a little bit different for a project which is not Tundra related at all, but a project which we have in eastern Norway, funded by the Norwegian Environment Agency, who really want us to monitor the long-term effect of wetland restoration. So this previously drained wetlands, it has now been restored, and they want to know what the differences in the carbon fluxes will be. And this can of course run over longer terms. Now, much of our work at the department is also not using only the established techniques that I was talking about now, but also develop new techniques. And here we recognize or acknowledge that our eddy covariance flux measurements, they are really meant to represent flat homogeneous terrain. They're not really meant for very complex terrain or heterogeneous fluxes, where you might have hotspots that you might miss with your eddy covariance tower, and then you might misrepresent this area. And then when you try and validate a global product, you actually validate it with a slightly biased measurement. So our idea was to use drones and basically fly drones over this area, measure gas concentrations and temperature, and then inverse model what we think the surface fluxes are like. And we have done this exercise and tested the potential in synthetic data experiments, where we just go into a simulation and place sensors in the simulation and see how well can we capture the true surface flux, which we know in these experiments because they are synthetic. And we've shown that with a handful of drones or so, you can actually estimate the surface fluxes without much bias and with a similar accuracy as eddy covariance. So here you see how we do this in real life. So you see this nice video by Pim, where we have 3 drones in the air and measuring these profiles of temperature, humidity, and wind speed. And you can really see how these measurements now, they represent a larger area. So this drone basically picks up signals from the area that you see here. And this is now really on the same scale as a global Earth system model or climate model. So we are still working on this, but we are hoping that our technique can really help the field. One other advantage with that technique is that we can explicitly represent complex terrain. So we can, in our wind simulation, we can put in the topography. You can take any topography that you like. You could, for example, take a terrain model like this one and simulate the flow over it, and then put your drones there and see what kind of signals you measure. And these signals, they would then explicitly account for this topography. And this is, of course, very helpful if you have areas like this, where there's probably a lot of CO2 and methane coming out, but there's no way to place a chamber there on a representative spot, or really put an eddy covariance tower there, which would not measure on this scale. But if you fly a drone through here and actually represent the topography, we can probably assess this much better. So that's the plan for next year. It was the plan already for a couple of years, but the COVID pandemic didn't exactly help for that. Good, this was that. Then here, this is a new project that we just started together with the D-Science Center and the Institute for Technology Systems, where our idea is that these drones that you've seen so far, they were just pre-programmed. We just told them where to fly and told them a flight plan, but there was really no intelligent system. There was no intelligence in this swarm. These drones, they could probably collaborate much better. They could say that if one drone checks out this spot, then no other drone has to go there. Or if one drone finds something interesting in one spot, maybe the other ones could follow after. So we think that there's huge potential for introducing these collaboration with the drones. And here, now this video played a little bit too quickly. But here I did a quick proof of concept where you have this sort of surface flux map, and there's one hotspot there, and these 15 drones, they try to find it. And they are not only guided by their own measurements, but they are also guided by the other measurements. So they really learn from each other. And this is what Alouette will work on now for the next couple of years. Obviously, such projects, they need good drones. They need proper, dedicated drones. So we realized this maybe a year ago. And we got in contact with people at ITS and the Research Defense Establishment, FFE. And they are building their own drones for their own research. And they were so kind to share their 3D model of the drone and basically the specifications of the drone. Our job was to basically do this. And this little error there probably involved buying 20 different things from different companies in China and the US and assembling it all. So this is what my office currently looks like. And the idea is to build 5 of these drones now. We have built the first one and we have flown it at Finse. It is a really, really nice drone. And we really think that this could be a game changer in this business. Of course, this is such infrastructure or such equipment should now all be collected in this newly established drone lab. So the MATNAT faculty gave us funding to support drone research and teaching. So we can now really acquire more instruments, more equipment, both off the shelf and our own developments. And I should say that most of this is for aerial photography, for LiDARs and multispectral things, but also a small part about it is about gas analyzers and swarming. So this drone lab, which Claire is now working in as well, it is supposed to help all researchers at MATNAT to guide along these rules and regulations and help them with the post-processing. And now we also hopefully get a proper workspace so that our offices get a lot cleaner again. So, maybe I'm too quick, no. My conclusions are that next time when you're out skiing or hiking, you might think about these coupled dynamics of carbon and energy exchange in the environment, because understanding these surface processes are really important, especially for climate models where feedbacks are involved. And lastly, I think that we have quite exciting times ahead at this intersection between geosciences, statistics, and engineering. Thank you.
Thank you very much for this very interesting presentation. Now it's open also for questions. So anybody of you have a question to Norbert about his presentation? Please. Paul.
I was wondering about if you measure the wind, then embed a drone, then this drone creates a lot of wind by flying. So how does this work? How do you measure this, or how do you account for it?
It's a very good question, actually. Yes, so the drone creates its own downwash, but it still needs to navigate. The drone is placed in one position, and you use the GPS and the barometer to keep it at that one position. So the drone actually internally does a lot of maneuvering, about 100 or 200 times per second. It creates, or it basically accounts for the wind disturbance that it feels itself. And this is not a straightforward business. There are studies that show that you can use, for example, the tilt angle of the drone. If a drone that is supposed to hover in one spot, but there's wind blowing, it needs to tilt. So you can use, for example, the tilt angle to estimate the horizontal wind speed. You could maybe use the power that goes to each rotor to estimate the vertical wind. If there's an updraft, probably the drone for a few fractions of a second will need less power. So you could see that. And we detect all of this. We measure this at 100 hertz on our drones, which is actually part of the reason why we went away from the off-the-shelf drones to our own developments. It's exactly to have access to all of these log data. And now our task is to estimate the wind. And I think it's fair to say that it's possible, but there is surely some interesting questions coming up.
Yes, Regina.
Thank you, Norbert, for a very nice talk. You mentioned that at a point it goes from sink to source, the carbon, and how nicely this can vary in time. But what is your best guess for the entire Tundra on average? Is it a sink or a source?
That's a very good question. most likely, so there's actually varying research on this, and this depends a little bit again on the terminology. Do you mean tundra? Do you mean permafrost tundra? Do you mean Arctic tundra? So I think the answer depends a little bit on the terminology. No, but so historically it's clear that it has been a sink. The carbon has accumulated in the Arctic. We know that, and we see it just by looking at it. But now there's more and more studies coming out that claim that it has already turned from a sink to a source. But this is all overshadowed with this variability. You have this strong heterogeneity, you have a few point measurements, you try to upscale with a global product, but it's really, really hard because the variations spatially are so large that your little trend that there could be in this signal is oftentimes overshadowed, or it's very hard to see this trend. But yeah, we have shown that, for example, the winter time is now clearly a source of carbon. We see that. The question is if the summertime uptakes, maybe the carbon fertilization that we get from increased CO2, the greening in the Arctic, if these things contribute to a stronger uptake as well. And at least as far as I know, there's no conclusion about this.
Yes, is there another question? No, I have one question. Also you mentioned a little bit greening of the Arctic. The point is, of course, when you change it's going from a net sink to a source of CO2 or methane, and it's probably because of thawing of permafrost and things. But the vegetation is also changing. How is? Also I've heard about that you get bushes instead of small tundra plants, so you get higher vegetation. How is this impacting the system?
In numerous ways, yeah, and it all comes back to these coupled cycles of energy, water, and carbon. And because these shrubs or bushes that you mentioned, they both become taller, they become denser, they spread out in space. They colonize areas which they previously didn't. So these are actually three different kinds of greening, I would say. And then when they grow, they catch more snow. When they catch more snow, just the wind-driven snow, they warm up the ground because thicker snow depth insulate the ground better, such that maybe the permafrost underneath it starts to thaw more. And all these coupled things, they accelerate. And again, I'm not sure what the net effect of it is, and if you can model it very accurately 100 years into the future. This is a big challenge.
Okay, there is a question in the back, and now I'm not going into the back, so you still make the question and then you repeat it before you answer.
Yeah. No, this is a very good point. You kind of replace one problem. Oh, sorry. Yeah. So Colleen was asking that eddy-covariance towers. Yes, they sit there. They give you one estimate, but they measure year-round, 24/7. We have gaps in the data, of course, but they have good coverage. With a drone, you get one snapshot. You have one flight. You may be airborne for half an hour or an hour, and then you estimate one flux or one time. You might resolve spatial heterogeneities. You might see the boundary layer structure a little bit better than you see in the eddy covariance data. So it has some advantages, but you only get these few snapshots, unless you do some kind of automated drone system where you shoot up drones regularly on an automated basis. But this, as of now, in the rules and regulations in Norway, certainly this is not allowed anyway. So this is also not what we're aiming for, and we are not even aiming to replace eddy covariance. We are very happy with this technique, and we think it's extremely valuable. But we think that we can probably learn more about this, also biases in the area, if we, for example, fly around these eddy covariance towers and see that this tower, which has been standing there for 10 years, actually didn't measure that hotspot, which was just a few hundred meters away from it, then that would be really nice to know. But you're absolutely right. You're kind of get different problems with drones.
Okay, thank you. Now I don't see any more questions, and then I have no need to keep you here. Once more, thank you very much to Norbert for this very nice presentation. And then I wish you welcome again back the next year, because then we also have Geo-Unstags, but I don't know exactly when and who is presenting. We will come back to that. So welcome back here next year, and Merry Christmas.